Hello. My final project is a navigation case study, visual odometry using CNN-LSTM state estimation. Developers of the software systems used to guide the behavior of self-driving cars, UAVs, and robots invest heavily in deep learning methods to solve challenging navigation problems. Automated vehicles rely on sensing devices, primarily camera vision and LiDAR, to provide information to the vehicle to estimate its precise position in space-time relative to other objects in its environment and to where it is on the Earth. In this case study, I focus on changes in pose as extracted from binocular camera images. The data come from the Kitty Vision Benchmark Suite dataset. The approach followed in this case study is a CNN-LSTM model. It is implemented in Keras, but uses a very much reduced data set in order to deal with computational constraints. In this case study, I highlight some of the important considerations in working with camera image data to produce quantitative estimates of poses. These considerations include choice of image resolution, time step size, and whether to use full images only or in combination with image differencing methods. In addition, I illustrate how to create both X and Y training sets when you need to aggregate sequences of frames over a time dimension. The Kitty repository can be accessed at the web link shown above. This is the one for the odometry dataset. There are other challenge datasets that you can find. The entire RGB color image data is nearly 64 gigabytes, so it takes a long time to download. About half of this is useful for training a model because it includes ground truth values. Out of the 21 video sequences, the first 11 have ground truth files associated with them. Below you see an example of an image from the data set. Each video sequence represents a short car journey. And I should mention that they are filmed at 10 frames per second. Pose measurements come in the form of a flattened 3x4 vector known as a camera matrix. The first 3 columns of this vector, once you reshape it, represent rotation around X, Y, and Z axes. So, and below at the bottom you see an example of this for the first training observation. So think pitch, roll, and yaw in an airplane. The fourth column represents translation, so think X, Y, and Z coordinates in a Cartesian plane along with elevation. And from this you can of course estimate velocity and bearing. So we're interested in how these changes over the course of a vehicle's journey and whether we can train a model to infer them from sequences of images. The data processing for this case study involves really four main steps. Well, actually 5, because first you have to obtain and organize the data, in this case from the Kitty repository. You can also use the miniature data set that I have supplied along with the IPython notebook. You then need to process image data in pairs of consecutive video frames, and this may also include possibly downsizing images, finite differencing the images, and stacking images, all of which are made much easier if you use the OpenCV CV2 Python library as I did. In addition, you need to process ground truth data, which is in the form of a text file with 1 observation per line and no headers, no line numbers, and you need to make sure that it aligns with sequences of images. Ordering is all important. Next, you need to allocate the processed images and ground truth to training and validation sets. Before you can actually model this, then, you need to transform the images into vectors and the ground truth text files into vectors for your X and Y inputs. Image size is an important issue in this work. The raw images are probably on average 800 kilobytes, and you can see the dimensions there. So at 10 frames per second, 10 seconds worth of images amounts to 80 megabytes already. There are trade-offs in this. Of course, larger image sizes, more pixels contain more information, which is better for the eventual model that you want to develop. But of course, it requires a lot more computation and much longer processing times. I tried both an Amazon Web Service EC2 machine as well as my own MacBook. On the MacBook, a reduced size of images of 4,500 samples at 310 by 94 was taking nearly an hour per epoch. On the Amazon Web Service computer, I started getting messages related to GPUs being exhausted and would every so often have to restart the Jupyter kernel. To create a small sample of images that could be reduced to less than 20 megabytes for this assignment, I reduced the original images by a factor of 6 and provided just 270 pairs of stacked images. This, of course, did not help in terms of training and validation performance. Time steps are another important issue in this type of work. The preferred method for analyzing these data is to group frames into subsequences representing a longer time step. 100 images, for example, represents 10 seconds, and researchers report using 100 to 800 step protocols. So a 100-step protocol implies that each observation is represented by 100 images. So you basically group those vectors together, those tensors together, and a single ground truth reading from the end of that sequence. The trade-offs are, of course, smaller time steps are prone to error and overfitting, especially if you use 1 second or less. With larger time steps, you're going to get better, lower error rates. However, then there are fewer sampled observations, but each observation has more information because it's comprised of multiple images in sequence. Of course, with larger time steps, computation times increase for each observation, but there are fewer observations for the same amount of physical data. However, fewer observations is actually a problem as well. So the researchers that I reviewed report using the full set of ground truths, nearly 30 gigabytes, and some even augmented them. The coded demo that's included with this case study features the IPython notebook, which you see listed there at the top of this slide. It includes extensive data processing routines with error checking to implement the steps that I just went over. The CNN-LSTM model is written in Keras. There are also functions for analyzing results, predicted paths. The miniature data set that I provide mimics the Kitty data set setup, as you can see there in the image at the right. It includes a small set of images, full set of ground truth files, and the Kitty developer kit, which includes C++ evaluation code that is used to evaluate the performance of models submitted by contestants. Processing video frame images typically, well, at least in my implementation, involves 4 steps. First, there's selecting pairs of consecutive images at times t and t-1, downsizing them, which is almost always desired to reduce the computational burden. And then optionally, one method is to take the finite difference in pixel values between 2 images. Another method is just to use the consecutive images as they are. Either way, you wind up stacking images one on top of the other, as shown in the diagram below, where I've actually used the finite difference method. So the lower image represents frame at time t, and the differenced image above that is the difference between that one and the previous image at time t-1. Next, we need to create training and validation sets. Ground truth observations are in a text file, and these are specific to either training or validation sets, but they need to be paired up with consecutive image frames from the appropriate folder, all of which need to go through the downsizing, finite differencing, and stacking steps. So it's very important to make sure that the ground truth observations are aligned in order with the image files throughout the data preparation process. And in my notebook, I've created several checks to make sure that this process is working properly. Next, you need to vectorize the images and the ground truths. So for the X values, I used on the images OpenCV2 to create these four-dimensional tensors. The shape of the X tensor should be of the format samples, time steps, dimension 1, dimension 2, and channels. Ground truth files need to be processed so that the last pose position in the step sequence becomes the observed outcome for that time step. So with those, you collapse the time dimension. You wind up with just two deformat samples and labels. It took me a while to figure this out, and it was not at all obvious from a lot of things I read. So then you need to check to make sure that you're getting the right dimensions out of your data, and I do that in my code. All right, now we get to the model specification itself, which was actually inspired by at least 3 different research papers and sets of authors. Here I've listed the one that I've most closely followed, the deep VO method of Wang and al. At Cambridge University. As you can see, they're inputting pairs of stacked images, running them through a series of convolution layers, then through the deep recurrent neural network using LSTMs, then through a set of fully connected layers, and then finally there's some post-processing, which I did not do. Here's how it's implemented in Keras in the IPython notebook. One of the keys to this is using a time-distributed wrapper, and it took me a while to figure out how to make this work properly. But eventually I did get it working. And to really know whether or not I have the right number of, say, neurons and layers and so forth is really subject to further testing on larger data sets. One other thing I did, I'll just mention here, I developed a custom loss function based on the Wang paper. It puts proportionally more weight on the rotational part of the pose data relative to the translation part, and that seems to lead to better fitting. Unfortunately, working with this small sample size for this demo and reduced image resolution and wanting to be able to complete this within a reasonable time period resulted in not very impressive training accuracy. But again, this is, I believe, largely a function of the small sample size and poor image resolution. Nevertheless, the loss function was pretty stable over multiple runs. And when I tried this with higher image resolution and more samples, I did get much better training and validation loss, sometimes in the single digits. So another check on this that you will always do when you're dealing with spatial data is to plot trajectories. So I've written custom functions for plotting trajectories as well as calculating cumulative distance. And what you can see here is that the predicted trajectory is so small you can't see it in 2 of the images. It appears as a little orange speck in the lower left and upper right images. But if we zoom in, change the scale and zoom in, there it is. It's just very small. All right, so in conclusion, inferring odometry measures from camera images using deep learning methods is very challenging. Other people have done it successfully, and so I believe that I could too, given enough data and computing resources. There are fundamental trade-offs between computing resources and accuracy, which are driven by image resolution, size of time steps, and sample size. Again, successful developers have used a lot more data than is used here. And some have also used pre-training and multi-step approaches, auto-encoding images, or post-processing with Kalman filters. To refine the approach used here to the point of usability would require a similar level of investment. Nevertheless, I think this is a good start and captures the basic logic needed to develop such a model given sufficient resources. Thank you for listening.